All right. Yeah, thanks for this chance for me to share some of the work that I did last year at Curtin Uni. As the title says, the project is about analysing data from agricultural experiments, particularly large-scale on-farm strip experiments, and I'll talk about what those are in just a moment. So over the next 15 minutes, I hope to give you a brief introduction to precision agriculture, explain what is a large-scale on-farm strip experiment, and what makes them distinct. I'll briefly describe a couple of approaches to modeling data from those kinds of experiments and comparing those results from those methods applied to some real and synthetic data. And finally, I'll wrap up and give you some recommendations and open for questions. So in a nutshell, the main premise behind precision agriculture is that since the characteristics of a farm or a field vary spatially, any kind of additives such as fertilizer, pesticides, irrigation, for example, should be applied in a varying manner to accommodate those varying ground conditions. So here's an example of a wheat farm. This is in Kojonup, about 270 kilometers southeast of Perth. And you can see from the different pigmentation that clearly the wheat growth on this farm is not uniform. And so as a farmer, if I knew that some zones responded really well to additives like fertilizer, while others not so much, then I could save a lot of money and resources by targeting my efforts. And so just on those areas that I know will respond. So as a farmer, there are generally two questions that I'm interested in. First, which areas of the field should I target for the greatest effect? And what exactly are those effects going to be? And so the first I'll call treatment effect estimation, and the second I'd call yield prediction. Now, bear in mind, whilst there may be many reasons why, biologically or ecologically, why a treatment effect might vary across the field because of soil composition or because of drainage, things like that, our objective here is just to identify where those are and quantify the effect size. And so how do we go about profiling the response of a field? Well, you have to conduct an experiment, of course. So here is the same wheat farm, but overlaid with a schematic of an experimental design. Now, farmers are not interested in differences between points in the field that are just a few meters apart. Typically, wheat farms are hundreds of hectares, and so it isn't practical to attempt to target small patches of field for intervention. So this large-scale experimentation is what sets on-farm strip trials from small plot trials. And in this case, the strips are about almost a kilometre long and about 50 metres wide, and the different colours indicate that different strips have different concentrations of fertiliser applied to them. And at harvest time, yield monitors mounted on combine harvesters collect information about the yield at every single point in the field. And so using that yield information, we can therefore then go and feed a regression model and get these beta zeros and beta ones. Now, of course, and also there'll be an error term. Now, the catch here is at the scale that farmers operate, we expect all these parameters to vary by location. Because as we said earlier, the effect is not going to be uniform across the entire field. And we call that spatial heterogeneity. And that typically comprises two components, non-stationarity and autocorrelation. Non-stationarity basically says that we can't fit a global model to the field because these beta coefficients are going to change with location. And autocorrelation says that each location in the field is not completely independent of all the others. Points that are nearby are going to be similar to each other, basically. And different geostatistical techniques differ in how they handle these two components. And speaking of autocorrelation, here's an example of a variogram, which is one method of modeling the autocorrelation in spatial data. In geostatistics, there's this principle that points that are closer together spatially are generally more related than those that are further apart. And this is what is shown in this particular figure by this curve. On the horizontal axis is the distance between 2 points in, say, a field. And on the vertical axis is the semi-variance, which is you can think of as the inverse correlation. And each of these points that you see on the graph corresponds to a pair of spatially separated points in our field. And we see that as we consider points that are further and further apart from each other, their semi-variance increases or correlation decreases. And eventually we reach a threshold around a distance of 775 in this example, where it plateaus out. And what that's saying is that for this particular field, points that are greater than 775 meters apart are effectively uncorrelated or independent. And the reason we need variograms is because an estimate of autocorrelation is often needed for some geospatial modeling techniques. So now I'm going to talk about two popular techniques in literature regression Kriging, and geographically weighted regression, or GWR. There's a reason we call it GWR, it's a bit of a mouthful. So regression Kriging is basically estimating some value at an unobserved location S0 by taking the weighted sum of values at observed locations Si. And notice how it comprises two terms: a global regression term where the beta coefficients are constant across the entire field, and the second term for modeling the residuals using these Kriging weights lambda. And this framework can accommodate autocorrelation effects by bundling them into this residuals term. But it does assume stationarity, since these beta coefficients are considered uniform across the entire field. The expression for GWR also has beta coefficients, but these are estimated using data not everywhere, but from a local window around a point of interest. And that window is specified by a kernel function and bandwidth size. I'll talk about those a bit later. And notice, in contrast with Kriging, GWR does handle non-stationarity by allowing these coefficients to vary spatially, but autocorrelation ignored because all the residuals are assumed to be independent. Now, at the scale that farmers operate, both non-stationarity and autocorrelation are expected to be present. So we can't probably just use either or. We're going to instead use sort of a hybrid method that combines both regression Kriging and GWR, which we'll call GWR plus K. So what is GWR K? Well, it's basically applying GWR followed by simple Kriging. So having first applied GWR to get yield predictions and treatment effect sizes, we continue to Krig the leftover residuals, which should now be free of any non-stationarity. Having Krigged the residuals to model their autocorrelation, we proceed to add these residuals back into the original prediction to improve its accuracy. So it's quite straightforward. So we conducted some computational experiments using a data set that's freely available in R. It's from a Cornfield experiment in Argentina in 2001. On the right, you can see how 6 different concentrations of nitrogen fertilizer are applied to a field, 3 replicates for a total of 18 strips. And on the left side, we have the yield of corn at harvest, which you can see varies quite a lot along each strip. It's clearly has heterogeneity in it. So a simple way to compare the accuracy of 4 methods is to use a data splitting approach. On the right, we see that we've randomly masked out about 50% of the values of the yield, and we try to recover those values using 4 methods: simple Kriging, regression Kriging, GWR, and GWRK. Accuracy was then expressed in terms of mean absolute error and root mean square error, and we repeated it 40 times to get some idea of the distribution of the errors. So here are some examples of the outputs. Remember, we did this 40 times. This is just one particular instance. Top left, again, is the known observed yield. Top right is the simple Kriged yield. And bottom left is the GWR predicted yield. And we see that simple Kriging interpolates the field quite well in comparison, but GWR seems to smear out the finer detail. And we'd expect that because, as mentioned earlier, GWR fails to accommodate local autocorrelation effects. However, once we add back in the Krig residuals, we get a much better result, which we see in the bottom right. So numerically speaking, if we look at box plots of the mean absolute error, we see that aside from GWR, which is significantly worse, as we saw from the previous slide, all the other techniques have similar prediction accuracies. We might have a hazard guess and say that perhaps the precision of GWRK is a little bit better, given how narrow the IQR is, but that's just me speculating and perhaps being hopeful. So that was yield prediction. Now let's look at treatment effect estimation. For this experiment, we synthesized some data so that the ground truth would be known. And we did this by choosing beta coefficients and treatment rates that are comparable to real-life farming values. In this case, we have a constant beta 0 or 5 tons per hectare across the entire field, and that varies across 3 zones with the intention to simulate non-stationarity. Lastly, we simulate 3 different treatment levels, and these are arranged as 3 strips with 3 replicates, each 600 meters long and 25 meters wide. And in the bottom right here, we have this composite yield before we add any noise. And so to make it more realistic, we do start adding 2 components of noise. First is zero mean IID Gaussian noise, and the second is autocorrelated noise, where the values within a particular row or a particular column are correlated with each other. And so once we add that term all together, we end up with this final synthetic yield data on the right, which now contains both non-stationarity and autocorrelation, of which we have the ground truth for. So for the experiment, we use the entire data set, so no data splitting, to fit a regression model using regression, Kriging, and GWR. We then proceeded to compare those estimated beta coefficients with the ground truth, recalling that beta 0 is constant at 5, and beta 1 changes across these various zones. And indeed, as a farmer, I'm most interested in the beta 1 because that tells me how effective my additive, like my fertilizer, happens to be. So here are the results of this simulated experiment. As expected, the regression Kriging just provides a single global estimate because it doesn't allow for non-stationarity. And it unsurprisingly just gives us the average response across the whole field, which is 0.025 tons per kilo. In contrast, GWR does return a spatially varying result. You can see by sort of the patching. And recall there were 3 distinct zones with their own beta 1 coefficients. And looking at the box plot, we see that in each zone, GWR recovers a pretty good estimate of what we know to be the ground truth, which corresponds to these dotted lines. Just for completeness here, the results are fitting beta 0, and they're not as interesting. I just wanted to point out that for GWR, which is this panel on the bottom here, we can see that the autocorrelation shows through with these patches. So it doesn't handle that very well. And you might also observe that along the top edge here, there's sort of edging artifacts, because remember, GWR uses this kernel, and the kernel sits outside of the field, and you're going to get some kind of numerical weirdness. So given these results, I've summarized our recommendations as follows. If all that is needed is yield prediction, then regression Kriging would be fine. And that's why it's very popular in literature. But when it comes to estimating treatment effects, or getting these beta 1s and beta 0s, particularly in the presence of non-stationarity and autocorrelation, then the hybrid GWRK gives you better results because it will give you a spatially invariant result. So just one more result before I conclude. You might recall earlier that I mentioned GWR has 2 hyperparameters related to the kernel that you use, the kernel shape and the kernel bandwidth. For these experiments, we went with the boxcar shape, basically a binary mask centered around the point of interest, mostly because it's very popular in literature. However, the choice of kernel width is interesting in the context of strip experiments. Recall that in our synthetic example, each strip was 25 meters wide. So that means we should choose a kernel we shouldn't choose a kernel that sits completely inside one treatment strip and not overlap its neighbors. Otherwise, any regression coefficients are going to be unreliable. And conversely, since the whole field is about 600 by 225, if I pick a bandwidth radius that's much larger than 100, I effectively cover most of the field and get a global estimate, which kind of defeats the purpose of using a windowed method like GWR. So we investigated the effect of kernel size by rerunning the analysis but with increasing bandwidths, and the results are shown here. The ground truth for each of those 3 zones are the dotted red, green, and blue dashed lines. And you'll observe 2 phenomena in these box plots as we increase the bandwidth. First is, as the bandwidth increases, you'll notice that the variance of our estimates gets smaller. And second, that as with increasing bandwidth, the point estimates start drifting towards the average of the whole field. And neither of these is surprising, since we know that as the bandwidth increases, we're pooling more data, so we're going to get more precise estimates, as it were, but at the cost of drowning out the local effects in favor of a global estimate. So I've said today that precision agriculture promotes efficiency and sustainability by helping farmers target their interventions. On-farm strip experiments are conducted at scales where we cannot ignore spatial heterogeneity, and that heterogeneity is mostly explained by non-stationarity and autocorrelation. GWRK approach is a good approach for getting yield predictions and treatment effect estimates in face of that heterogeneity. And if you are using GWR, then you need to take care with selecting your kernel bandwidth. Thank you very much.